This video will be about continuity in business calculus. Continuity, in the guided notes on limits, there was this graph. This is a graph of a piecewise function. Notice there are two holes in the graph. This means that if you were traveling along the function and approaching the hole at x equals 2, then you would fall through the hole instead of continuing traveling on the graph. Similarly, if you were traveling near 4. Now consider if you're traveling from just 0 to just 1, or from 1.5 to 1. In this case, you can travel past 1 with no issue. In this case, you can continue past x equals 1 with no issue. Traveling by x equals 1 introduces a concept called continuity. So this graph is continuous at x equals 1, but is discontinuous at x equals 2 and x equals 4. Notice that at x equals 1, the limit exists, and the function is defined, but the limit does not equal the same value as the function value. And for x equals 4, the limit exists, but the function is undefined. This helps to define continuity. The limit of a function at a, limit as x goes to a of f of x exists, f of a is defined, and the limit of x goes to a of f of x equals f of a is the definition of continuity. State where the function f of x equals x squared minus x minus 2 over x minus 2 is discontinuous. So, suppose the limit as x goes to 2 of f of x equals 3. But f of 2 is not defined. So the function is discontinuous at x equals 2. There is also a hole at x equals 2, but this is because the function is undefined at this point. In a piecewise function was created that defined f of 2 to be 3, then there wouldn't be a hole, and the function would in fact be continuous. This means you can fill the hole and remove the discontinuity. So this discontinuity is called a removable discontinuity. Think of it where the city fills a pothole. They were able to remove the hole in the road and make the road continuous. Similar idea here. So now example number 2, we want to state where this function is discontinuous. So the solution is there's a hole at x equals 2. So it is discontinuous at x equals 2. The limit as x equals 2 of f of x equals 8 if you approach equals 8, and f of 2 equals 3. But since they don't equal each other, the function is discontinuous at x equals 2. So the limit as x goes to 2 of f of x does not equal f of 2. In this case, there's a this is removable discontinuity. At x equals 4, the limit doesn't exist. So the function is discontinuous at x equals 4. So in this case, there's a jump in the graph. Think of this as driving along a road and all of a sudden the road drops off. This has happened in the last few years where bridges have fallen while cars are driving over them. This is not a good thing to happen. So discontinuity can be a bad thing. So x equals 4 is called a jump discontinuity, since you must jump to get from here to here. Example 3, we want to state where this function f of x equals minus x plus 3 all over x squared minus 4x plus 4 is discontinuous. So the solution of this is, as 1 travels along towards x equals 2 from the left, the function is heading towards positive infinity. As 1 travels towards x equals 2 from the right, the function is also going to positive infinity. However, the limit, if a limit is positive infinity, then it doesn't actually exist. So the limit as x goes to 2 of this function is positive infinity, but that doesn't really exist. So this function is discontinuous at x equals 2. This function is called an infinite discontinuity. All right, notice that the last example, the function was continuous everywhere except x equals 2. The domain of this function is all real numbers except for x equals 2. This is also where the function is discontinuous. So the function is continuous at all points in its domain. This gives an insight into other functions. All polynomials, rationals, exponentials, and logarithmic functions are continuous over their domains. This means that one can find the limit of any point in the domain of these functions by direct substitution, substituting the point into the function. This is because the limit as x goes to a of f of x is in fact f of a for any continuous function. So our last example is number 4. Find the limit as x goes to 1 of 3x squared minus 2x minus 4. Since this is a polynomial, it is continuous over its own domain. So all I have to do is plug in 1 in wherever I see an x. So this would be 3 times 1 squared minus 2 times 1 minus 4, which is equal to negative 5.